Okay, so basic idea is we're going to take data that is structured or encoded in one manner and encode that data differently such that we can attempt to use less data or less space to encode that same data. We have two types of compression. Lossy compression and lossless compression. With lossy compression, the original data is lost, but the representation, that data is still sufficient to serve the purpose of what the data is representing. Yeah, the final goes over everything, but it's going to be like twice the number of questions. It's a 2-hour, 10-minute test instead of a 1-hour, 5-minute test. Okay. Lossless compression can get us all the way back to the original data state. All right, so JPEG, MPEG, GIF, etc. Well, there are a lot of media, various other media formats. And these tend to be lossy compression, where the original data is lost in translation. All right, so let's do some I'll do some various shapes here. Varying colors. All right, we'll save this image. So the least compressed version we're going to have here is a 24-bit map. The way the 24-bit bitmap is encoded is we have each pixel, 8 bits of red, 8 bits of green, 8 bits of blue for that particular image. And so we've got our 24-bit map, 24-bit image takes 4.2 megabytes. But this data is fully here as best as it can be rendered in an image, right? So we'll go down all the way down to each individual pixel, and the pixel is either white, black, yellow, whatever particular color a given pixel is. It's basically a massive array. So we'll have in the file the very first pixel at the top, and then each pixel right after that in a massive array. The metadata of the file will just basically tell us how long a row is, so we know when to wrap the pixels down on the next side. Difference between size and size on disk. So the size, so that just should be the internal fragmentation. Right, this number is probably divisible by 4086 type thing. Let's see. Let's see if we can divide that by 4086. Not quite. What's my 2 to the 12? Did I get my number wrong here? 4096. Thought. All right, so it's 1080 blocks on disk. This disk has a smallest unit that's going to work with, just like a 32-bit system, right? Make an int or any other smaller integral type. 32 bits of data is going to be its word size. So the word size on disk is 4096. So I fixed my math. And so that whatever 600 or 700 bytes there is not actual data, but it's occupying part of our disk space, right? So that's our internal fragmentation that we talked about previously. All right, so what we can go and do is we can compress this image by changing the encoding. So we'll look at all these various items here in JPEG, 24 bits to JPEG. We can save it. And, right, not really much changed. Pretty much looks just like it did before. But down here you see at the bottom of Paint, now it's down to 70 kilobytes. Let's see. Probably won't be able to see it on the screen share, but right up here at above the tip, there are some gray pixels of data. Some artifacts got introduced into our data file here because of the lossy compression, but our image is quite simple enough that whatever data loss or data introduction that happened when we encoded this image, it's as far as the user is concerned, right? It is still the 4-point star and a pentagon overlapping, right? They pretty much can't tell much of anything. Right? And get the original back up here. Right, look at them side by side. There's not much to tell that they're being different. I think the red is slightly different, but that could just be my imagination. And we have a few other options. GIF version. Seeing that we might lose some color. Right, this one's giving us a lot more artifacting here. And we zoom in to our yellow, we can see that there's an extra color that's been added in here. Basically, to try to get the color to match, they didn't have our exact shade of yellow in the color palette. That is a GIF, so they basically blend in yellow and orange to approximate that color. When we're far enough away, it's not particularly noticeable for me on the 4K monitor. I can see even at this distance that we have a bit of texture going on into both the green and the yellow. Right? It's added data here to try to approximate the colors instead of just swapping out an entirely separate color. All right, so it's a lossy compression, but all right, 75 kilobytes. It's a lot better than our 4 megabytes that we started off with. Let's go back to my original data. And we got TIFF and ping. I can never remember what HEI stands for. All right, TIFF's doing pretty good here, down to 20 kilobytes. And I'm not seeing any artifacting at this layer. Let's jump in. All right, not looking too bad here. The yellow might be a slightly different color. Right, the yellow on the right seems slightly lighter. That's even coming through, right? The stream that's going between me and you is compressed. I don't know if it's using gzip or what compression it's using to get the data across from you to me, all that fun stuff. And of course, this is my JPEG on the left. I should get this back over to the bitmap. We're comparing the true original versus the destination. Right, so just because we're losing data doesn't necessarily mean we're losing anything important. It all just depends on what the data is, right? If we were trying to compress financial records, lossy compression is probably not a good idea because we need to get back all the way to where we started in that circumstance. But there are plenty of situations where compression, right? Streaming, whatever you're streaming, it's going through compression. I don't know if you all watched the last season of Game of Thrones, but there's a particular episode where it's like practically unwatchable because you can't see anything. And the story behind that one apparently was that because of the compression of the streaming platforms, the the data got a little bit too far lost. So it's still on my to-do list to watch that in the uncompressed version, see if we can see anything useful or not. All right, ping portable network graphics down to 20 kilobytes. And so if this were a file on the file server, you gotta present it on your web page or whatever like that, 20 kilobytes or 70 kilobytes versus the original 4 megabytes. And there's a lot of space saving going on here by running it through a compression. You're with me so far there. And compression rate. The rate is going to be a percentage. How well the compression worked. All right, so the formula is length of the input minus the length of the output divided by the length of the input. All right, so we had, I'm just going to round it off to 4 million. The Weissman score to measure data loss, there probably is. There, if I knew it, I no longer recall what it is anymore. Look at the 19700 one. All right. Oh, that divided by the 4 million. So we had our 4 megabyte bitmap versus our 19.7 kilobyte TIFF image. And we'll get the calculator back out to do some math. All right, so we got point, which equals the same number. All right, 0.49, 0.5% of the original size. I got that backwards. I forgot to subtract my 1. Get my calculator back out. Let's try that again. Yeah, I forgot to do the subtraction first. All right, so we got 99.5% compression. which is pretty good. Obviously, 100% is going to be the impossible maximum, right? You can't compress down to nothing. Something must exist. Compression rate could also be negative. Sometimes things don't go as well. But on the other side of things here, right, we have another way to go about this. What we can do is use even lower levels of bitmaps. So instead of 24 bits per pixel, we can go down to 8 bits, right? 256 colors, that's 8 bits, 2 to the 8 is 256. And often each time we do this, we'll get a warning about color loss, right? And the yellow got darker. We made the change here, but we're now down to 1.4 megabytes, right? We got a 67% compression rate instead of 1 byte. Excuse me, instead of 3 bytes per, we use 1 byte per, so 67% compression for all our various pixels. And we can keep on going. Make the bitmap further and further colors, right? So 2, 4, 8, 16, 4 bits. 4 bits of color here. At the compression rate, there's no one. So for whatever the size of the input was, right? So we'll do the compression here. We got our 4 megabit, 4 megabit, 4 megabyte, 24 bit map at 4 megabytes versus 4 megabyte 26 color bitmap. All right, so if we want to look at the compression, compression rate going from 24 bits per pixel to 8 bits per pixel, right? That'll give us, and since they have the same number of pixels, we can just do the 24. 24 minus 8 divided by 24. And 0.667 equals 66.67% compression rate, aka it's 1/3 the size. The compressed version of the file. Here we have in my size order, our original data, whole scale 4320, and then we got our 26 color bitmap, 1/3 that size, and then this one's half the size, right? 1444. I don't know why that's just saying 722, but Windows is hiding some of the details from us in this particular view. Right, the full size on disk, and this number here should pretty much be half the number. There is metadata as well inside the image that tells us, how many rows and columns, all that stuff. That's going to push us slightly off 50% compression rate. Right, we'll do the math since we got the numbers there. All right, so let's get back to our original actual numbers. Versus our 4-bit. 740, 422. Lost some data along the way there. Let's try that again. Guess I didn't have the 8 highlighted or something. Let's try that one more time. There we go. Not that we can't have negative compression rate. We'll see that in a minute. All right, so 83.25. Percent compression rate. All right, so going back, right, original data, compressed data, right? So we're losing data. What we're doing here, our bitmaps, is there's a standard color palette that is associated with the image. So the image is going to say, what's my color palette? What is my dimensions? And then it translates given value for each pixel and then picks from the color palette, appropriate color for that. All right, so there's no this shade of orange or this shade of yellow, however you want to look at it, that we have in our original on the left-hand side. So it's taking us the closest color they come up with. As we keep on going down and down, how many bits per pixel? All right, 1 bit. All right, so you off or on. So we're going to go monochrome, black or white. All right, and the data will be as it is. Because our image was pretty simple, we can still figure out the idea of what the image was and make things out. So if we really, really need to save space, not that storing this as a bitmap is at all really a compression algorithm, you can see the size of the file is still huge by comparison, 182 kilobytes versus 70 to 20 range we get with our actual compression strategies. But it is a simple substitution. We just map each pixel from the current unencoded value to a replacement value on the other color palette. So it's a straight one-for-one mapping. But of course, the original data is completely lost, right? We have absolutely no idea from this image to figure out what the color was inside the star or what the color was inside. Yeah, that's interesting. It's like magic. It just disappears on me. Inside our Pentagon here. All right, so if they lost less compression, go about taking the plain text into the encoded text in such a way that the encoded text can be brought back to the original state. Let's take a look at, we trigger some network. It doesn't want to. All right, reload. All right. I'm forgetting where it says things here. Typically, we will see gzip being mentioned here for the web compressing things, but they've been dev toolbars changed so many times since I've used it heavily. I can't find it anymore. But right, the code that's driving this page, there it is. Finally found it, content coding. All right, so it's been sent through a gzip. So on the server, right, this particular file, which they've added a name in front of it for, not too sure what the numbering is, right? I don't work at Google, so I don't know what they're doing the numbering for, but this content generated the server side from some other file, dynamically generated, however it's generated the file. And the file has all kinds of fun code and other data points in it. Right, we have some JavaScript keywords here, return, array is array, all fun stuff. Some of this stuff we can read because it hasn't been minified because you can't minify the keywords with JavaScript. You only minify the variables and all that fun stuff. Really, it's one way to do compression. Even before we went through gzip. And so this is effectively the original data on the server after it's been minified. Minified mean originally this was probably called varcat equals alpha dot Fahrenheit or whatever the names of the variables were in the actual source code that's in Google's source repository. Then it went through minification because single character variable names are just as good as 20 character variable names from the computer's perspective. The computer doesn't care about how readable variable name is. It's a variable name. It just means the location in memory once that variable is brought into existence. So we had multiple rounds of compressions. The first compression, which was a lossy compression, was minification of the JavaScript data such that the code is as lightweight as it can be. Right? Certain things have names in them that are part of JavaScript itself, and JavaScript language itself isn't minified. I'm kind of surprised actually they don't have a minified JavaScript engine. That would give us some extra savings on space. But anyways, then this data went through gzip on the server. All right, and they're caching it in their web farms somewhere. And that data was sent down to us. And then on the client side, on the browser, on my machine, it decodes that gzip format and decompresses it back to this minified version of the code. And let's see, where is that? All right, it'll look something along these lines here after it's been prettied up some. Anyways, compression, heavily used. I can't remember how old gzip is. It's around 15 years old or something like that. It's one of the newer things. This is one of the areas where I did have history down there. Well, that is a very brief history. All right, let's go to Wikipedia. Oh, that's been around longer than I thought. I remember being used that long, but right, you can see that even the versions of gzip keep changing just from a few months ago. All right, data compression is very big because if a website takes a long time to load, you're going to tend to lose customers. And businesses like to keep customers, not lose them. So it's going to be doing things to help expedite. Actually, reading a Google book a while back. Talking about how in the earlier days of the web, they would have like rounded corners around boxes and things like that. What they would do is they'd download just one image that was one corner, and then in JavaScript, they would rotate the image 3 times, make the other corners. That way they can, that's 1/4 the amount of data needed to download this corner, because way back in the earlier days, CSS couldn't do rounded corners and things along those lines. It was all very heavily image based to give a non-blocky feel to the presentation that you're seeing, right? So lossy, lossless, all that good stuff. Please read this page. There's a lot of discussion here using things that you're using pretty much every day, right? The web technology stack is in heavy use. And even if you're using apps on your phone, right, tend to be some sort of web-like engine sitting behind it. All right. All right, so there's a lot of different ways we can go about compressing things. We are not going to cover them all. Definitely not enough time for that. But we'll get through a few items. All right, so ASCII. ASCII. American Standard, whatever it stands for. Code for information exchange, right? So the symbol table, it just means the bit pattern for 65 is capital A. Unicode, 16-bit symbol tables, table. Same idea, probably mentioned on this page here. Right, the first 256 values are the same, and then we have more. Right, so if we have text-based file, right, so all files are binary. Doesn't matter if it's executable, dynamic link library, bat file, text file, code file, whatever. It's all on disk binary, right? Computer does not, the hard disk does not understand the character A versus character Z versus question mark. That's just different bit patterns that we abstract to mean something else based off of the encoding. Right, so right now, if you look at the bottom right here of Notepad, it's saying UTF-8 is my default encoding. Let's see. Switch back to school domain over here. Where are we? 2023. All right, TF8 encoding. But we have other options. Down here, just using plain old Notepad, we can change what our encoding is. So I lost my 8 part there. I'll go over 16. UTF-16 encoding. And let's see. Probably need more data in my files here. We'll see what Windows shows us. It's going to give us good data here or not. 36 bytes and 17 bytes. All right, good to go. All right, so both files have the same information. So yep, Notepad++. No, we don't want to update. All right, run through. Which one we got there? That one, 16. All right, compare the two. And says they're identical, right? Except for the encoding. So we look, same thing in Notepad++ down the bottom right here, UTF-8, UTF-16, but the way they're stored on disk, not the same. right? Because one's 17 bytes and one is 36 bytes, even though they're exact same data points in the file. So again, metadata. We go find our online hex editor, was hex edit or hex it. All right, we go check out our files. It shows, let's see. I'm forgetting again. Let's open up the other one as well. Should we get on that one? UTF, let's open up. 16. All right, so when we look at our payload of data here, a text-based file versus where we got a couple of extra bits of data here, then we get to our a text-based file. Right, so our first text file, it's just assuming, it's presuming an encoding format. So looks like UTF-8 is defaulting because we don't have any actual header data. Right, the A, 61 here, 97 decimal is the very first thing that shows up in the file. But over here, the A, it's not the first thing that shows up. Right, we have additional bits of information inside the file, metadata header, whatever you want to call it. That's describing how the file is being encoded so that it knows that the 61 and this 00, that's all the A character, or at least that particular first character in the file. All right, so we have a bunch of wasted space here because we're not using anything in the extended part of the symbol tables space. But we have support for simplified Chinese, Greek, Cyrillic, whatever other characters that are part of Unicode because we're using an 18-bit format. Does that kind of make sense? And those are our standard, some of our standard tables. And there are others. And so in the context of compression, we find we can use a custom symbol table in place of a standard one. All right, so basic custom symbol table. All right, we'll simply collect all of the used symbols in the data that we want to compress. And using a serialization strategy, create a custom table. All right, so say we're doing, let me get the calculator out so I can get my zeros in the right place here. Go back. And whatever, we'll just do a star, wherever star, do a 0. Know what that one is. All right, so let's say that's this above table represents all of the symbols in use in our data set. We can use the 8-bit format to encode the data, or we can create our own custom table, right? So ASCII, Unicode, right? They're both built on the same the same pretty much approach. Okay. All right, so all the way at 0, you get an image off this page here. And let's go back to ASCII. All right, so all the way here at 0 bits, 765. So we got 0, 0, 0, and the bits 4 through 2, 1, 0, 0, 0, 0, right? We have the null character. And then so 0, and then we got 1 is whatever so is, right? A bunch of control characters for the most part, backspace, bell, horizontal tab, whatever. But it's just a serialization pattern. We have 0, 1, 2, 3, 4, 5, 6, right? That's just one number right after the next. And so we're just talking like bits. We got 0, 1, 0, 1, 0, 1, 0, 1, right? 0, 0, 1, 1, 0, 0, 1, 1 pattern. 4 zeros, 4 ones, 8 zeros, 8 ones, so on and so forth. Straight serialization scheme. So the underlying bit pattern that represents capital A or lowercase a, right? The only difference between our alpha characters is 1 bit, right? They're in the same row, so the last 4 bits are the same. The only difference is our column here, we have 1, 0, 0 versus a 1, 1, 0. All right, we have 0, which is 48, 32 plus 16 bits. And it's just a serialization scheme. But if we're not using all those symbols, right? If this was our data that we wanted to compress, right? And we've got a whole lot of repetition of the same data. Whenever you have patterns in the data, just like what we have with our bitmaps, right? The same pattern, even if I go back to the original 24 bits, right? The same bits are showing up over and over and over and over and over again. In a repeated fashion. We'll look at run length encoding as well. That do a pretty good job compressing it until we get to this area, but the same patterns being repeated over and over again. And there's only what? 1, 2, 3, 4, 5 colors in all of this entire image. So if we wanted to create a symbol, custom symbol table for this and still be able to retain all of the original data, where we do our color palette, 0 is white, 1's black, 2 is yellow, 3 is green, and 4 is whatever shade of red that my palette offered up to me that I selected. And we could still do, at that point, do a pixel by pixel, 3 bits per pixel and have full color data there. And even at that point, we'll have repeated data over and over again, and we can further compress our data. Right, so between repeated patterns and limited usage of the particular characters, right, we've got E being used quite a bit here. Right, 255 times for E. Right, 170 T's, so on and so forth. Since I copy pasted the same thing over and over again. All right, B a bunch of times. All right. All right, so this is the basic approach. Just see all the symbols that we're using, and then do a replacement. All right, so our compression rate here, right, we're using a fixed length, so both the standard symbol tables, and the basic custom symbol table are using a fixed length encoding scheme. Every X bits is a symbol, aka character, to be decoded. All right, so the advantage, the standard symbol tables, is that they are well known, such that we require little to no data, as we saw in the header of the file. To indicate which symbol table is being used. The custom table will have to include net data into the header. Right, so there was a good long while, like impossible to play DVDs on your computer, or at least it was particularly difficult. You had to have the right codec, decodec, fun stuff, which is basically encoder, decoder, because the DVD file, right? It's an encoded data file, right? And you have to be able to decode it, translate that decoded data into pixels and sound to be presented on the screen. Which means you have to have the actual codec or decodec to be able to process that data file. Not that people much care about that these days because pretty much just stream everything. But even so, however, Netflix and Amazon, Hulu, whatever, Max, however they're streaming the data down there, they're definitely doing it in a way such that A, it's compressed, and B, in such a way that you can just save the data off and then be able to upload it and have other people watch the same videos, at least now without jumping through hoops, because they're doing similar things. I wouldn't necessarily call it security, but it's sort of along those lines there where they might even throw some encryption there. I have no idea. Protect streaming content, but you have to have a reader. So whatever the writer is that is being used, corresponding reader must exist such that we can decode the data stream back to consumable data. All right, so with our custom symbol tables, we will make a reader here, but our compression rate for the above, right, we had 8 bits. 8 bits per symbol, less 2 bits custom symbol divided by the 8, giving us 75% compression rate. It's not bad, but it is not the best we can do. All right, so above we had our fixed length code words, variable length code words. There's other ways to go about things. All right, so this is how many years? 100, 150, 1820. Oh, we're 200 years now. All right. All right, so Morse code, same idea. So we have our symbols, A through Z, and then 1 through 0. All right, so it's an even more limited symbol set that we're using here, but it is a variable length encoding scheme, right? A is only 2 symbols, or two length code word, B 4 length code word, so on and so forth. One of the things about Morse code is it tried to optimize, right? So remember the history, right? I think Morse, they take, I don't know, section of the Bible, or took a book and basically more or less count letters, see which letters are used more often than the others, sort of thing. And those that are shorter, like E, right? So we got E at 1. There's a T, yeah, T is at 1 symbol. We got dots and our dashes. So it's easier to encode an E and a T as opposed to encoding a Q, right? Q is 3 long pulses with a short pulse in the middle there, along with a pause. That's the other problem. Morse code is a punctuated encoding scheme. We have to encode a letter. All right, so we're going to encode, all right, happy. Right, we would get H, so that's a bunch of dots. We got 4 dots, then we would pause, and then we get a dot dash, and then we got our P, wherever that is. Dot, couple dashes, dot, dot. Do it again. And RY. All right, and we had white space in between each of these so that we can know the difference, right? Because a dot and a dash, right? That could be an E and a T if there was punctuation between these two, right? So all of a sudden it becomes changed from happy to be, oh, happy, whatever. And we changed the meaning quite significantly by adding that little bit of punctuation at one point in time. So it requires punctuation. So it's basically a ternary code. We have dots, dashes, and pauses, and that makes up the encoding of the message, right? So seen a Western, seen someone at the teletype machine. Go back. Oh, that's why it's not working. Right, one of these old doohickeys attached to a line and just more or less complete the circuit, send a pulse. Right, so they found a way to compress the data so that it could be sent long distances over a pretty quick time. All right, so the reason why we need the pause is because of the way that this symbol table is built. It's not observing. All right, so Morse code, which is the ternary coding scheme, dots, dashes, and pauses. It does not observe the prefix clause in its encoding scheme, which is why I require pauses to let us know that we are at the end of a symbol. All right, so let me move this on. Okay, move this on to the next one. Huffman code. Huffman code. It's going to be a compression algorithm. We'll create custom symbol table that uses variable length code words. All right, so our algorithm. Step 1 for each symbol, create a tree with that symbol as the root along with its frequency in the data set to be encoded. And when we say encoded, we mean compressed as a synonymous term. We're going to go ahead and we're going to combine or rather while we have a forest, combine the two smallest trees based on the total frequencies into a new tree, the root holding the sum of the frequencies of its two children. All right, after we've completed the forest, what we're going to go ahead and do is assign there. Okay, we're going to assign 0 to the left branches and 1 to the right branches to create the code word for the symbols that are at the leaves. All right, so given the following data, generate generate the code words. All right. And we'll just arbitrarily do A, B, C, D, E, F, or A, B, C, D, E, since I don't need 5 rows here. And some arbitrary frequency. So whatever data is that we want to encode, this is how many times A shows up in the data. There's 27 of them in no particular order, 12 Bs, 9 Cs, so on and so forth. And we'll combine these together. Get a screenshot of that. Go to drawing mode. I am going to keep the forest nice and ordered here. All right, so we have C with 9 occurrences. We have B with 12 occurrences. Going back to original data, D at 15. A at 27. And E at 31. All right. The first thing we're going to go and do is we're going to take our two smallest trees, and splice them together with a new root. So we went from a forest, and a forest of 5 trees. Then we went ahead and combined the two smallest. And now we have 4 trees left in the forest. Right, and we will repeat the process. Going to separate it out a little bit here. All right, so when we insert the new tree back into the forest, we will want to maintain it. Just keep things organized in sorted order, right? Keeping it sorted. Grab the smallest two. Right, because that makes it quite easy to grab the smallest two when the data is sorted. It is simply the first two. All right, so we'll grab our two nodes, add them together, and then we will reinsert it back into the forest. All right, so we have A and E. And DCB. All right, rinse and repeat. We will combine smallest two. So we've got AE here, 58, and insert that back into the forest. All right, repeat again. Take the two smallest, of which there are only two. And then we'll join them back together. And what's our combined at that point? A94. All right, let's redraw the whole tree now. All right, so we had DCB, which I believe was D and 15 over here. And that was a CB. What was CB? 21. Which had its two children. And then over here we have a couple of children as well. C at 9 according to the table, and B at 12. Again, this is in the previous steps from combining things together. Don't have them all on the screen at the same time at the moment. All right, A, let's say 27 and E at 31. All right, so we'll have zeros. The left branches to use to build out code words. And we will have ones or right branches to build out our code words. Right, so the code word for D, the way we get to D from the root is just 0, 0. So we have code word for D is 0, 0. Then we have 0, 1, 0 for C. And next up we have B there at 0, 1, 1. A is 1, 0, and E is 1, 1. All right, and there's our symbol table. So if we go back, add a column. All right, A was 1, 0, B 0, 1, 1, C 0, 1, 0, D, and E. All right, now that we have our custom symbol table, we can encode the data. All right, so for each symbol in the table, we look up for its code word and output that code word to the stream pressed file wherever encoded data is going. All right, so all right, let's just say our encoded data was A, B, A, C, D, D, whatever. A is 1, 0, and I'll just put a space here just so it's easier for us to see. The actual encoded data wouldn't have any white space. All right, B 0, 1, 1, A 1, 0, C, D, E, D. All right, and this would be the binary. Binary encoded data. All right, so if our code word was deed 0, 0, 1, 1, 1, 1, 0, 0. All right. Bead, whatever words I can come up with. My limited set of symbols. And 0, 0. Decoding. Using the tree that we had constructed, we'll read a bit from the data stream. If that bit is 0, traverse the tree left. That bit is a 1, then we'll traverse right. upon encountering a leaf, will output the symbol and reset to the root of the tree. All right, so let's copy our tree. All right. Let's see, that's our encoded data. All right, so we read A0 first, so we go left, our first 0. And then we read a 1, so we'll go right. And then we'll read a 0, so we'll go left. So our first output is a C. Reset back to the root. We have a 0, so we go left. Consume that 0, we have a 1, go right. And we have a 1 after that, we go right. And we've encountered a leaf. Output that symbol. Output that symbol and go back to the root. We have a 1. So we go right. We have a 0, go left. And we have an A. Still have data on the input stream, so we'll reset to the root. Where we have a 1, 1, 1, 1, so we have an E. And then we have a 0, 0, or a D. For our last run through. Yeah, whenever you can't go any further, that becomes your first symbol. And reset back to the top. CVAD. All right, so. All right, let's go ahead and decode that. Give it a moment, and then we'll see if anyone has anything. Anyone able to decode what is our first decoded symbol? All right, we got a 1, 1, so that's an E. What's next? All right, well, 0, 0, that takes us to D. And someone said Eddie 80. Sarah, sounds about right. Keep on going. 0, 1, 1. That takes us 0, 1, 1. That takes us to B. Is this what other people are getting, or did I goof up already? 0, 1, 1's a B. Yes, no, maybe so. No clue. All right, we're in agreement so far. All right, so what's after B? Yeah, it's easy to go. It's definitely one of the ones we want to cross it out, move along, cross it out, move along. The missing, right? So next up we have 0, 1, right? 0, 1 and 0, 1, 0. So that's a C. 0, 1, 0. And we've got our 0, 0 for a D. And then a 0, 1, 1 for a B. Did I goof up? Did I cross out too many myself? I'm just kind of going down random branches myself, so I didn't pay attention to what the original word was. Let's cross check. Right, the other way to do it is from the table. It's a little bit more of a ponderous approach. There, we got a 1. All right, so it's either an A or an E. All right, we got a 1, so it's an E. Right, so we got our first bit there. So we can go ahead and space it out. Help easier to track our work. We've got a 0, so it's one of these 3. We've got a 0 after that. So that's this one here. We hit a leaf. All right, so we got our add part. 0, 1, 1. 0, 1, 1's our B. We got a B. 0, 1, 0 is our C. We've got a 0, 0 for D. And a 0, 1, 1 for a B. And so we'll undo those. Make sure we cross check our work. If all of a sudden we're halfway through the tree and we still we ran out of bits, then we've run into an error. Something went wrong. That's one of the things we'll be talking about next week. Error detection and correction. What happens when you get extra bits in the payload or a bit gets flipped from 0 to 1 or 1 to 0? Data can get all messed up real fast when noise is introduced onto the line. All right. Questions about Huffman code at the moment? All right, so we've got our input size. We want to calculate our compression rate, see how well we did. All right, we had 94 symbols in our data. So we had 94 times 8. That's 752. My brain working. And not scientific mode. 94 times 8, 752. 752 bits of unencoded data. Output size. Take the frequency of each symbol and multiply by how many bits that symbol takes. and sum total for all symbols. All right, so we have 27 A's times 2 bits per A, right? That shouldn't say symbol, that should say code word. My table's all messed up. Copy pasted that, so that means the bug was in multiple places. All right. Right, the code word for A. Every time we want to encode an A, I have to output 2 bits of data, a 1 and a 0. All right, so that is 4 bits. We have 12 B's times 3 bits for B. Okay, 36 bits. 9 C's times 3 bits for C. 27 bits of data. What we got? D's are at 15. 2 bits. And 31 E's. Tim's gotten here. Times 2 bits per E equals 62 bits. Here's our total. Definitely cheat with the calculator. 4, 36, 27, 30, and 62. Let's try that again. Since I hit the wrong key. 54 plus 36 plus 27 plus 30 plus 62. 2. All right, 209. Double check my data entry skills. 30, 62. Right, so we have 209 bits of compressed data. All right, so length the input minus length the output divided by length the input. 72 less than 209. Try again. 72 less than 209 divided by 752. All right, so we got 72.2% compression rate. Let's take that comparison further and compare that against a simple custom table. All right, so with our simple custom tables, however many symbols there are, we have 5, so that means we're going to need 3 bits, and 2 3 is 8. So we just use the fewest number of bits, that gives us enough possibilities to do it. All right, so our custom table, 4 or 5 symbols will require 3 bits per symbol. So we would get, 8 minus 3 divided by 8. 5 8 is what, 62.5%? 62.5% compression rate. All right, so we improved upon it. We got better by a small amount. And the idea behind this is things that show up infrequently get longer code words than those that show up frequently. All right, so 31 and 27 will end up higher on the tree. We only had 2 levels here in this particular sample set of data. But DCB, and E, right? These are my leaves. All my leaves happen to be on 2 levels in my binary tree. Those that are at higher levels will have higher frequencies, where higher is going towards the root. So we have C and B here down at the bottom, and the way they ended up at the bottom is because we combined them first. Since we combined them first, they're older members of the tree, and they end up sinking further and further down the strata of our tree here. That's the idea of Huffman code. I think we'll go ahead and take 5-minute break, and then we'll do another example. All right. Let's add another symbol and change some of our numbers here. Let's see. Just trying to look into the future here, see what my numbers are going to be. All right. See if that works out. All right, so we'll build our forest. First step, we have C at 11, B at 12, who's next? A at 22, F at 23. Let's skip someone. I skip my 15 here. D15 and then E52. All right, so combine our two smallest ones. So we've got CB at 23 and then everyone else. Needs to be dropped in proper sorted order. Now, you'll notice we already have a 23 in the tree. So depending on how it is we're maintaining this ordered list, that would drive where the 23 is going to end up. What right could be done, right? If we just keep a sorted array, a super low tech way of doing things, right? Grab two values and then shift things around. Things aren't particularly ideal with that. We use a sorted linked list. That's not too bad, right? Getting the two values off list, that's easy enough. They can happen constant time, but then there's the next value, right? It's going to have to work its way down the list and then, bridge the gap. Most likely, not necessarily, but we'll use just a min heap to track these data, right? Because we just create trees, F1 trees, min heap to track this stuff. And build our min heap, just start dropping the values in, and the smallest value works its way to the top. So when we ask it for the two smallest values, I just say delete from the heap and then delete again, and I get my two smallest values. And then we can insert that value again into the heap. And when we're inserting a value, we do insert from the end, and then it works its way up. Right, so since we're inserting it from the end, working its way up, the tree that gets inserted, if will stop when it sees the value larger than n. F is not necessarily its parent, but from that kind of perspective, the way that the data is going to be ordered, this is how we'll differentiate when we have duplicate values. Right, so the tree that's being inserted will be to the right. Generally, on the test, I try to avoid duplicates because it creates a potential ambiguity issue. As long as there's a convention to eliminate the ambiguity, it's not ambiguous anymore, but there isn't necessarily one right way to fry the egg. But when we do have duplicates, right, dupe value is to the right of the matching value. Yes, yes, what's the word? Who needs it? Okay. So put that on its own line here. All right, we'll keep on combining. We have our existing forest of values, and now dA at 37 is going to get plopped back in there. Our forest of values with our 223s coming 46. FCB 46 gets dropped in there. All right, E52. And then we get our DA FCB at, what is that, 83. Got it in, and then we have our massive node at 135. Everyone with me there? Okay, this is the same work as we were doing before, just not all drawn out. But we will draw out the tree now from the data set. Because a tree is definitely easier to see than a whole bunch of text. Just flopping around there. Then thousands of words sort of thing. All right. EDFCB. Two nodes as children. We had E. All right, just looking at the line above it. Probabilities don't much matter here when we're drawing out the tree. We could put that in if we wanted to, but what matters is the structure, because the structure is going to determine where the zeros and ones are going to end up. All right. We've got our def, which is the DA and FCB. DA, FCB. And the tree grows and grows. You'll notice that E is pretty high up here. All right, so FCB, we can expand that one first. Since that's on the line above, definitely being too radically generous with my space here. So let's shrink that a bit. FNCB. So annoying when the lines aren't attached. All right, FCB. And CB is just CB. Slightly smashed together, and we have a DA over here. Now, just copy C and B and D and A. Right, and we get our zeros and one, right? So E is just 0 for a code word. D would be 1, 0, 0. A is 1, 0, 1. F will be 1, 1, 0. Where's that? F, 0. 1, 1, 1. Forgot a couple lines here. 0 and 1, right? So we got 1, 2, 3 ones, a fourth one for B, and C had a 0 at the end. Fix my image. Got a couple lines. Not that I'm sure you didn't have it all figured out based on that, but here's our symbol tables ranging in length from 1 bit to 4 bits. Right? It will take what 48 bits to encode the 12 Bs. It will take 44 bits to encode the 11 Cs, and it's only going to take 52 bits to encode the 52 Es. Right? Even though there's still more than double the number of E's in the dataset versus B and C combined, it's not taking anywhere near double. Right? It's practically on par with those two symbols because it occurs so often. It found itself with a quite short code word. And it's the only one that starts with 0. Right? It doesn't exist as a prefix as anyone else in the tree. And the reason that is only the leaf values. All of our leaves are our terminal positions. There are no symbols on internal nodes. Right? If we were to build a tree for Morse code with dots on the left and dashes on the right, right, as soon as we have our first dot, we would have a symbol, right? It was E or something like that, and then a dash was T, whatever it was, and then there would be dots and dashes going down in a binary pattern, because we just use a binary tree to represent Morse code. Problem is, leaves are not anything indicatory. That just simply means the longest code word. However, the longest code word is, that's how many levels we're going to need in the tree type thing. It's only when we encounter that pause, that where we are in the tree, that's the symbol we use for Morse code, and we reset back to the root. Right. So similar principles will be in at work or in play for a lot of things in compression. Right. Many algorithms, especially those have been around for a long time and have seen improvement over the years, are often tweaks to the pattern. But every so often, someone comes with an entirely new approach. The new approach, we find different ways of doing things. Right. So whatever the code words are for our Huffman tree, the encoding and the decoding, it's the same process. Nothing changes. The encoding, decoding, the only difference is the actual code words that are part of it all. And one of the things we're not counting for our compression rate, we're just kind of tossing aside, is that actual header, right? We would need to encode the custom symbol table into the header so that whoever is decoding the data knows how to decode the data, because any given Huffman encoded data would be different from file to file. So I could take 20, 30 different files and then throw them through the Huffman compression algorithm, and each one is likely to have its own and completely unique symbol table, unless there's just a large overlap in the patterns of data in my files. But different files will very likely have different symbols in them and different frequencies for those symbols. That kind of makes sense? All right, let's tone it down a little bit. Run length encoding compression. All right, so run length encoding, it's just going to be a simple pattern analysis in a one-dimensional mindset. We'll let's do the algorithm. Read a symbol. Set the count of that symbol to 1. Read the next symbol. If it is the same symbol, increment the count. Otherwise, output the previous symbol and its count and update current symbol to the 1 red and set its count to 1. And I like to use apostrophe when I was not supposed to use it on its. All right, so let's say our data is number of A's, couple of B's, a few more A's, toss a handful of C's in there, and D, E, F, whatever. All right, so we will read 4 A's. And they'll output the run 4A. We'll read 2 B's. That'll output 2B. Read 3 A's. Output is 3A. And then I get 6 C's. 6C, 3 F's. All right, read 3 F's. And it's a 3F. 2A. 2C. 2D. And 2E. And then 2 F's. So our encoded data is all of what I just said, all in a line. 2A, 2C, 2D, 2E, 2F. All right, so side by side where you can see, assuming we have a monotype font here, my data has compressed. We have trimmed a little bit of the fat. All right, so we can get our compression rate. All right, we're always assuming ASCII. So we have what here? 4, 6, 9, 15, 18, 20, 22, 24, 26, 28. 28 symbols at 8 per symbol. We're going to have 28 times 8, 224. I forget the bits per. Equals input length. Output. Assuming 8 bits per count and 8 bits per symbol. We'll count the number of runs and multiply by 16 bits per run. And so we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 runs. So we have 10 times 16 equals 160 bits. For the length of our output and our rate. All right, same equation. Do the math. All right, 28.6%. Lost my decimal place there. All right, not terribly exciting compression. And let's do that again. Not what I want. All right. Let's see, my data is 4Fs followed by 2Es. What is that encoded? Guesses are more than welcome. There's no harm in guessing wrong. It's just a chat. All right, 4F, 2E. Pretty much what I said, right? We have 4Fs and 2Es, and encoded it's 4Fs and 2Es. So if we have A, triple BA, what is that encoded? All right, 1A, 3B, 1A. All right, so we have a run of 1, which ended up getting increased in size. 3Bs, we get 3Bs, and we get 1A again. Let's look at our compression rate while we're here. Column. Our compression rate. All right, here we had 6. Here we have 4. All right, 6 minus 4. I should spit it all out. 6 minus 4 divided by 6. All right, 33%. Here we had 5. Our output, 1, 2, 3, 4, 5, 6 is 6 divided by 5. And here we have negative 20%. It got bigger. Sometimes the data just doesn't want to play nice. Right? The way we calculate compression rate, same regardless of the algorithm. Or if you run WinZip, some zip tools will actually show you what your compression rate is as it's doing it. A long time since I watched one compress, but back in the days, be like, oh, we got good compression in this area, not so good compression in this area, and how did I get 6? Right, because we got 1, 2, 3, 4, 5, 6. We have 3 runs, each of which is 2 bytes. Right, so I did this all in bytes over here. Using bytes to represent it. In fact, let me scale that up to be bits so that we are consistent. 48 minus 24 divided by 48. Because bits is where we're actually moving to next. 30 minus 48 divided by 40. Yeah. Question, let me be consistent here, right? Because we have 16 bits per run. 16 times 3 runs gives us 48. Now, Let's optimize. All right, the number of bits that we're using to encode the counts need to be 8. It could be more, or it could be less. All right, we can play with it. So let's, yes, could be more, could be less. Let's take a look at some scenarios. Encoded data and well, let me use my raw data. Raw data, encoded data. We have a few options to go here. Encoded with 4 bits. Encoded with 3 bits. All right, so say my raw data is 27 A's, 40 B's, 16 A's, 32 F's, whatever. All right, so this is the raw data. It's just shown in run length encoding sort of pattern here. Okay, 4 bits. So 4 bits. Or 2 to the power of 4, right? So we get 2, 4, 8, 16, 32. 32 has the max count length. All right, so pretty much the raw data and the encoded data with 4 bits looks the same. 3 bits, 2 to 3, that's not a caret. Field 16 has the max count length. All right, so that means this 27, this 32, those are beyond what we can encode with 3 bits. What we have to do is repeat. So instead of just saying 27A, we will say 16 A's followed by 11 A's. 40 B's. Yes, that's 16 B's. And actually, there's a 40 in there. I did the previous one wrong. That's 32 B's followed by 8 B's. Let me separate the runs out since we're getting beyond nice evenly sized pairs. It gets harder to read. Punctuation, who invented that? All right, so we had 40 B's. So that's 32. And then 8 more. And going 16 A's, so we can do 16A. And then 16 F's and 16 F's. Can we get the fit? Squeeze, squeeze. No. Oh well. Good enough. All right, so how big? How much space is this taking? All right, so now we have 4 plus 8 bits per run. So we have 12 bits per run. We have 1, 2, 3, 4, 5 bits. 5 runs rather. So 12 times 5 was 60 bits of data. Originally, 27, 67, 77, 83, and 83, 1, 83, 85, 115. So we had 115 symbols, names 8 bits. 920. Did I? Oh, I totally did. All right. Very, very much right. I got my bits wrong. So what happens when you count on your fingers instead of using your head? Thank you for catching that. Okay. Here we have 3 plus 8 bits. Run. We got 11 bits times more runs. We have 1, 2, 3, 4, 5, 6, 7, 8. All right, gives us 88 bits. And let's compare that against encoded with 8 bits per. Right, basically we have these as runs 1, 2, 3, 4. 4 runs times 16 bits. Run equals 64 bits. All right, so with 5 bits, based on this data, we are eking out a little bit more performance. With 3 bits, I have to fix my math here. That's now 5, so that's 13. That's a 4, that's a 12. All right, 65. We did not improve. My math is wrong somewhere. Because 1, 2, 3, 4. 1, 2, 3, 4. 5, and this one had 4. Should have had some improvement here. Do. Or perhaps not. Maybe I made my runs way too big. Let me double check. 1, 2, 3, 4. Yeah. Didn't gain any improvement with that sample data. Let's do another one. A little bit more variance. All right, 27 A's. 12B, 3C, 2D, 2F, 1A, 10 B's, 10 B's, 7 A's, 6 C's is the raw data. Right, so, right, seeing a whole bunch of A's, type thing. Basically running it through the encoding to start, doing a run length encoding on it using our standard 8 bits, and now tweaking to see if we can't make it smaller. All right, so with 4 bits, or rather 5 bits, giving us our 32. Right, 5 bits is our smallest number of bits to be able to encode the largest run. So this one should give us a straight improvement. This original output, 16 times how many runs are 1, 2, 3, 4, 5, 6, 7, 8, 9. 944 bits, if my math is working. 5-bit output. Now we're looking at 14 bits and still 9 runs. Right, so 126 bits of output, right? Because when our largest value is 27, 8 bits, we got 0, 0, 0, right? The 128 bits not being used, the 64 bits not being used, the 32 bits not being used. So those first 3 bits of every single count is wasted space. Yes, it would combine, since I had my scale wrong there. 32B, thank you. And this becomes a 32F. Nope, those are 16s. Sorry, I looked at the wrong one. Let me undo. Those are 16s. Okay. Let's see. 5-bit with 32B and 8B combined. No, because 32 is as high as we can get. So we can't get a 40-bit. With only 5 bits, we would need 6 bits to do that. All right, so using 4 bits. No, we changed it to 4, to the 4. Oh, I didn't change all my 3s and 4s. There we go. Now my bug, I think, is gone. Yes, 32. 5. Okay. Yep. Nope. I was doing a good job confusing you with bad data on the screen. Okay, so 4 bits. Our max length of 16s. So this will change our encoding to 16As, 11As, and then the rest will stay the same. Output size equals 4 plus 12. Get ahead of myself. 4 plus 8, or 12. I have a math error here. 5 plus 8 is not 14. 117 bits. All right. 4 plus 8 is 12. Times 10 runs now, since we had one that got split into 2. All right, equals 120 bits. We managed to save 1 bit on each of these runs. Because our symbols are so fat, it takes an extra 8 bits. All right, so we added 11 bits of data in here with this extra run. We didn't have enough smaller runs to push us back to offset the other way. So we're pretty much going to get a bell curve for how small you can make the count for the extra number of runs is going to offset how much savings we are getting per run. Right, with the previous one, we're getting 13, right? So the original unoptimized, assuming just an 8-bit count, right, we have 16 bits per run. The easy optimization is just see what the largest count is and only use as many bits as we need to encode the largest count. And that was 5 bits. Right, and that saves us 3 bits per run. So we'll save 27 bits of memory compressing that. Going down smaller, that can work out. Right, if we go for 3 bits, our output size would bring it down to 11, but our runs are going to increase, right? Anything that's bigger than 8 will need to break apart. 8As, 8As, 3As, 8Bs, 4Bs, and we've got a 10B in here. All right, so now how many runs do we have? We just got to count out 2, 4, 6, 8, 10, 12, 14. Right, this, oops, 14, right? 140, 151. Where's that working right now? 11 times 14. 154. All right, so we're going the wrong way. Obviously, the fewer bits we go, we save on each run's length. My number of runs is growing. So it's right. We're trying to find where these two numbers are more or less kind of towards closer together so we can minimize the whole equation there. All right, let's see. Any questions about run length encoding at the moment? All right, we had the test last week. Let's talk about the test. That is opened up, right? You can see your results. Did I forget to do that? All right, you can see it. Good. So test 4. Oh, access code. Let's go grab that. Access is useful after all. Do 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 do. Don't know what I did before, but all right. Graphs, graphs, graphs. Big on Floyd Warshall, right? So that's p cubed. What degrees do wheel have, right? So we got perimeter and the number of vertices minus 1. You know, just draw a wheel graph out and just look and see what they are. Right, so we got 3, 3, number of vertices minus 1. All right, what's this one? Okay, A goes to B. B goes back to A, B goes to C. C goes back to B, C goes to D. D back to C, and then D goes over to E. And that's all E goes to, right? So it's nothing special. If we had one more edge, we could get a cycle graph out of that. Let's see. Well, can we do a bipartite here? Let's see if we can get a bipartite. So we've got A going to B, B going to C, C going to D, D going to E. We do have a bipartite. Well, let's change my answer there. Bipartite. I'll make sure the key's right on that one. I'll see you in a second. That is a complete graph. Everyone's connected, everyone except for themselves. That one's a cycle graph. 5 vertices, so it's not bipartite. There should be a star graph. B at the center. B connects to A and C and D and E. Star graph. All right, so let's build out our list. We've got A, which has B and C. We have B, which has A, C, and D. We have C. C has A, B, D, D has B, C, and E has D. Let's double check. Got 1, 3, 3, 3, and 2. A's got the 2. These 3 are 3. That one has 1. All right, so A, B, C. Correct. We should find lists are correct. All right, so A, B, C is correct. B, right, we're missing one that's wrong. C should be A, B, D, so that's wrong. B, C, E. E has D. 6. 6 only has 5. Oh, 6. Oh, yes, bipartite. Yes, yes, it's a star graph. I did forget to check those. All right, questions about number 7. Right. Sometimes people make a mistake with this bad one here, not properly alphabetizing. Otherwise, that's number 7. Number 8, Kruskal, minimum spanning tree. All right, let's build a tree. All right, so we have a 1 in here. That's not a B, that is a G, so we've got a 1. And we've got a DH. All right, the tree's not connected, so we're not done there. We finish our 1s. We have A, B. No cycle. Looking for 2s. FH. Looking for 3s. BH. Next. 2. No cycle though. CD. More 3s. Going for 4s. AH. Creates a cycle. No more 4s. Processing 5s. BC. All right. Creates a cycle. BC5CH. Right. That would create a cycle. GH. Cycle. Who are we missing still here? E's not connected in, right? So we got 5. And we've got EF. E's in the show. And we should be done at that point, right? Because GF, not new, DE, not new, EH, not new. All right, so these are the ones that were added, created, cycled, and had to be removed. And then we have 3 unprocessed edges. Questions about number 8 before I erase that one? All right, prim. First 4 nodes added after D. All right, so D is in here. In the table, we have 3 potential neighbors being added in the tree. First one is H. This edge is discarded. This edge is discarded. We will keep those edges. And closest one would be F. Discard that edge. Discard that edge. All right, so we have B up first because it's in the table. First. That discards that edge, and tells us about that edge. And then we get a 2 as being better than this 3 edge that we found a long time ago. All right, so we've got H, A, B, F, H. A, B, F, H. Questions on number 9. Okay, number 10. Euler, right? So everyone's got degree 2, so it's got an Euler circuit. Right, it has a trail. The trail is a circuit. And it's Hamiltonian, so everything there. Degrees of 3 and 4, so there's nothing Eulerian about it. And the Hamiltonian trail that we can make is also a circuit. Correct rows. All right. So AG is a 1. That looks good. AB is a 2. That's good. AH is a 4. BC at 5. BH at 3. And B's done. CH5. CD3. Got a bug there. That 3 is correct. And we have DH1. DH1. 1 and 1. Right, anywhere we're not a mirror across the diagonal, we're going to have problems. It's just a matter of which of these non-mirrors are problems. Assuming that we didn't completely mirror the bug, DH1, DH, DE. It's 8 rather, not H, DE. That should be an 8 there. EH7, EF6, EF6, FH2, FG8, and GH5. All right, so CD and ED are wrong. So which row is wrong? So we have the C row and the E row. CE. Presumed by no questions at the moment. That there are no questions for this question. Number 12. Okay, 13. Breadth first search. Ooh, these lines are nice and hard to see in dark mode. So let's go for non-dark mode, see if that works at all. No, that's not really. I'm sure you can see on your screen better, but it's connected out. I'll just draw it. Let's get the lines back in here. Invert number 12. Which rows are correct? Oops. Yeah, I did invert that. And spitting out the answer. Yeah, you'll have to message me on that one. You completely inverted it, and I can cross check. Okay, breadth for search starting at D. Backwards. Breadth first search. Right, so NQ, NG from the D row. AE and G are NQ'd. So that means A pops out as the second vertex. Number 2. That will tell us about B. E will be number 3. That'll tell us about F and H. Then G, number 4. We already know about H, so we go to B. B tells us about C. F tells us about I. H, nobody knew. C, nobody knew. And then I. And apparently we have our adjusted gross income here. AGI. All right. Questions on number 13. All right. All right. You look at two ways we look at them and see what patterns we have here. And we just start drawing it out. So first one, A goes to B, and it says B goes to A. So we've got arrowheads here. B goes to C, and C goes to D. All right, the fact that we have AB and BA listed means we have a directed graph. And let's try the next one out. Get AB. All right, we'll assume simple until we learn otherwise. AD, BB, all right, we got a loop to ourselves. And then we've got CD. All right, the loop to ourselves moves us into the pseudo graph. AB, AD, BD, and then BD again, and then a CD, right? So two edges between the same pair of vertices makes that a multi-graph. Questions on number 14. All right, 15. Which nodes are adjacent to C? That would be A and D. Which paths exist? All right, so does FA exist? FA exists. Does AD exist? AD, DC, DC, and then CB. CB. All right, so that's a valid path. BC is good. CE, not good. So stop there. BD, DA, AC, and then CF. CF, FA, AE. A doesn't go to E, so done there. AB, BC, CF, and then FB. All right, so 3 paths. Cut vertices, right? So cut vertex, if we cut it, causes 2 graphs. So cutting D, give us cut vertex. E wouldn't, right? A wouldn't, G wouldn't, H would, F would, and B would. Since we got a bit of a list going on there at the end. All right, so our ends, if A goes away, it's still one continuous graph. Same thing with C. E and G have redundant paths, so if one of those falls, the graph is still continuous. It becomes a nice straight line at that point. Depth first search starting at D. All right, so D goes the first one you can go to, which is A. A has one choice to go to B. C doesn't want to go to B because we've already been there. So, all right, we've got F. I'm sorry, I'm getting ahead of myself. We're at B. B is an option. All right, we don't want to go to A because we've already been there. So we'll go to C. So that's our fourth output. C has one choice, but to go to F. Now that we're at F, we don't go to C because we've been there. So we'll go ahead and go to E. 5, 6, 1 option, 7, like before. G's first in the list. And we have a CI. What's the difference between the first one and the last one? Is this for number 18 or is it number 17? Oh, that was for 14. Let me swing back to 14. All right. Multigraph allows multiple edges between pair of vertices, and the pseudograph allows single node loops. "19. Dijkstra. Until we found shortest path to vertex E, starting from vertex A." All right, so we stop. Once we know the shortest path from A to E. All right, so here's our goal, and here's where we're starting. So let's update the table. We can get A goes to F and G as the sources, 2, 8, 4, and 9. All right, and we'll take our shortest path. Building to B. B's in the loop. That 7's going to be no good. And we'll add in that other edge. Plus the cost to get there for 5. So F is up next. F is in the fold. That will tell us about this alternate route for 7. And this alternate route for 8. So E for 7 from F. And then G, F for 8. All right, so we have 5, 7, 8 to choose from. Right, E is still not marked true, so we'll keep on going. So we'll go to C. That path is known. A couple edges to take a look at here. 6 versus 8, so that's an improvement. You get to E from C, or 6 versus 7, that's an improvement. And we can get to D from C for 9. Those are the edges. And C was what we just did. So we have 9, 6, and 8. So we got to E, so we're done. And put X as the value for the empty ones. The extra credit, right? However you want to do it. There's a whole lot of ways we can do this. Right? Probably want some graph for traveling. Right? Carpools. Find the shortest paths from venue to everyone else. And then see, right, who are on those paths. Basically picking up people who are on your way. Extra credit is worth like 2 points, probably, maybe 3. All right, we can use a dictionary for the guests. Track their attendance. This, that, and the other. There's no specific answer that we're looking for. As long as you identify a data structure and explain why that data structure would be useful, then we'd be good to go. All right, where's my key asunder here? Oops, I clicked the wrong box there. It should have been complete bipartite. Bipartite. That was a misclick on my behalf there. GH. Where's GH in this mess here? F5. Yeah, I forgot to check that checkbox. Definitely knocked that 5 out. We got all the way up to 6. What else did I forget to click on? And I should have said this is false. Oops. Known as true or false, as per the instructions. So I can't even read my own instructions. Who needs to do that? Reading's highly overrated. You should just be able to listen to everything, right? Absorb through osmosis. All right, so it looks like the key is correct. I just simply have data entry issues on my side. All right, I'll of course need to grade the extra credit. And please ping me in Canvas if you goofed up on some of the answers where you like inverted the answer. You did the inversion, right? Get you like 3/4 credit back for doing the inverse, exactly the inverse answer. It has to be exactly the inverse. It just means you did happy instead of unhappy or vice versa. Looks like we've got the practice test scheduled for next week, so we'll talk about it next week. Yeah, message me on Canvas. So it shows up my inbox over here. Email is a terrible place because that just gets lost in the piles of email that comes every day to my IVC account. Right, Discord's faster, of course, for getting messages to me, but I don't know who you are in necessarily in Discord, so Canvas will track that. Okay. There's no more lecture tonight. We will go over the chaining lab after we go ahead and take a 5-minute break. So we'll take a 5-minute break and then we can go over the chaining lab. I'm going to add a run length encoding lab. Take a string, generate the run length encode, calculate the compression rate. And I'll pop that on there. That'll be due next week. Make a note to self, so I make sure don't forget to do that. All right, we'll take 5 and we'll come back and we'll go over chaining.